Thank you for joining us this evening for the third July Lecture in Physics for 2023. For those of you who are attending for the first time, this series has been running since 1968, and every Friday in July we have public lectures in physics here at the University of Melbourne, and it is something of a phenomenon that this many of you will come out in the dark and cold in the night in the middle of July to come and hear about some of the wondrous areas of physics that we study. My name is Susie Shea. I'm an associate professor here in the School of Physics, and this is my third year as the curator of the July lectures. And for those of you who've been attending, you'll also realise the lineup this year has something a bit unique about it. It's actually the first time we've had an all-woman lineup and a woman curator, actually. And another thing that I've changed a little about the format is we used to occasionally have a guest lecturer, but actually I'm working a little more to include the people who I think are some amazing speakers and thinkers and physicists from around the Melbourne area, since we do this every year in Melbourne. And so that brings me to tonight's speaker. Professor Virginia Kilborn is the Chief Scientist at Swinburne University, which is a very impressive title, but I'll leave her to explain it if she would like to. And also an astrophysicist, and she's going to be giving our July lecture tonight. And the theme this year was on the extremes of physics, and so hopefully that will take us to stars and galaxies and surveying the unseen universe. We shall see. So over to you. Thank you.
Thank you so much. Just want to do a mic check. Can everybody hear me okay? Yep, I'm seeing it. Okay, awesome. Thank you. Thank you so much for having me tonight. And as Susie said, coming out on a dark evening seems really appropriate for the topic. Before I get started, I'd like to acknowledge the traditional owners of the lands where we are, the Wurundjeri people of the Kulin Nations. Pay my respects to elders past, present and emerging, and of course that really deep acknowledgement that Australia's First Nations peoples were the first astronomers and bring a lot of knowledge to us today that we really value and use in many, many different ways, and we're learning more and more all the time about that. So yes, today I'm going to be talking about dark galaxies. I was going to just show you images of dark galaxies, but thought that would be a bit boring, so you will see some stars in here. And this is the first time I've actually dared to put the title of Dark Galaxies in a talk. I have given parts of this talk in various guises. You're going to have to bear with me as I explain a lot about galaxies as well, so that we all sort of get on the same footing. I've already done that, so we'll continue. So galaxies, they're typically found by the light from their stars, and so what we're going to be thinking about is what happens if there's a galaxy without stars. How could we find it, and in fact, is that a galaxy? So I'm getting a little bit whimsical. I am an astronomer. I'm going to take you on a journey of the unseen parts of the galaxy. But what I'm really going to talk about is, in particular, how radio telescopes can help us see the unseen parts of the universe. So many of you will, I assume everybody has left the city at some point and gone outside and had a look at the night sky. And the first part of my lecture is really going to be about what's a galaxy, how do we see them, how do we observe them, where do we find them. And let's start with our own galaxy, the Milky Way, this beautiful galaxy here behind us. What you can see is something, let's just see, sorry. There we go. The Milky Way stretching across the night sky. You can see light patches here, dark patches. We're going to find out what all of those are. But just to bring us all on the same page, our own galaxy, which we live in, is the Milky Way. We're looking at it edge on, and this is it here. So when we think about galaxies, let's just step back 100 years actually. where we had telescopes like this telescope here that Hubble is sitting at, the 100-inch at Mount Wilson. You could see really beautiful images from that telescope. They were quite often sketched rather than, we didn't have CCDs in those days. But we didn't know the distance to these galaxies. And in the 1920s, that was a real revelation to find that these small island universes or these nebulae actually were external galaxies to our own. And this was a discovery which was enabled by someone called Henrietta Leavitt, who is an amazing astronomer, and she studied a particular type of star, and a star like our sun, but a different star called a Cepheid variable. And like its name, it's a variable star, so the brightness of that star actually goes up and down over time due to various processes that I'm not going to go into in this lecture. But what she found out was that how bright that peak is actually related to how fast it is variabling, how fast it's varying. And so what we could actually then do is go, well, if we know how bright intrinsically the star is, but it looks fainter than that, we can actually work out the distance to that star. And so Hubble then had a look at these stars in this galaxy here, the Andromeda Galaxy M31, and found that it was external to our Milky Way. It was too distant to be in the Milky Way galaxy, so we actually knew galaxies are beyond our Milky Way. Not only that, Hubble, of course, found out that the universe is expanding. This is one of only 3 graphs in my talk, so for some that will be a relief, for some you'll be like, oh, I want to see more. But we can always chat about more in-depth things later. This particular graph is actually Hubble's original data from 1929, where he plotted the distance to a number of galaxies, and here they are here, and then their velocity, so how fast they're moving away from us. And we can actually find that from various methodologies. We can actually work out how fast the galaxies are moving away from us. And what he found was the more distant the galaxy, the faster it's moving away from us, and that the universe is expanding. And not only that, we found out even more recently that the universe expansion is accelerating. And so we found out a lot from that original data. And we have the Hubble's law, we have the, not the Hubble Bubble telescope, but I just love that cartoon, the Hubble telescope, Hubble Space Telescope, just really showing how important a discovery like this is. It's a really fundamental quantity of our universe, which we kind of take for granted now, but we didn't know really 100 years ago. So what I'm going to do is just step you through some images from the Hubble Space Telescope. And once again, we're talking about galaxies. We're trying to understand what is a galaxy, trying to get a feeling for that. And we'll look at Hubble telescope data because it's beautiful and it's the best, but also that what we're looking at are stars pretty much in these images. Not fully, like there'll be a few things that aren't stars in these images, but mainly we're looking at stars. So what we have here is a very, very big galaxy. This is M87. It's what we call an elliptical galaxy. There's no sort of prizes for guessing why it's called that. It's got it doesn't really have many features. Looks a bit like an ellipse. This actually does have a jet coming out of the centre of it here. But don't worry too much about that. For the purposes of this talk, we're really just focusing on the starlight. So this really diffuse area all around here, that is all the stars from this particular galaxy. Now in all the images that I'm going to show you, you'll also see these big bright lights here. And these ones are stars from our own Milky Way galaxy. So if we're looking at a more distant galaxy, we have to look through the Milky Way. And so we're always going to see stars in the foreground, unless we're looking at very small areas. And in that case, I'll let you know. Okay, so we've got an elliptical galaxy from the Hubble Space Telescope, spiral galaxy. So you might notice that it's called a spiral galaxy. Obviously, it's got spiral arms. And what we can see in a spiral galaxy is two things I'd like you to take away. One is that in the centre, okay, I can't get my pointer working, so what I will do is just gesture. In the centre, you'll see sort of an orangey colour. That indicates older stars. So stars that are older become redder because they become cooler, and that's just the way the spectrum works. And then on the edges, in the spiral arms, you see they're bluer. These are younger stars, they're higher energy, they're higher temperature, they're formed more recently. You can also see these dark tracks in this galaxy. And so now we're seeing another feature of a galaxy, which is the dust. So far we've seen stars and we've seen dust in a galaxy here. We'll move on. This is talking about dust. This is a spiral galaxy, but seen edge on. So imagine that for a previous galaxy and we've just tipped it on its side, and what you can see here is this beautiful galaxy from NGC 3717. Beautiful big dust lanes, really obscuring the rest of the galaxy. This is what we call an edge-on spiral galaxy. So it's just a normal spiral galaxy, we just happen to see it oriented on its side. So far we've got elliptical galaxies, spiral galaxies, and this is a dwarf galaxy. So a small galaxy, you can see this one is probably about maybe 1,000 or more times smaller than the first galaxy I showed you. And you can actually see the individual stars in this galaxy. So you can see them sort of picked out in this beautiful Hubble image. It's a very nearby galaxy. You can actually see some background galaxies as well. Up in the right there, that sort of red thing is a background galaxy. This one is, there's more dwarf galaxies than any other type of galaxy in the universe. So we've got to know about them as well. There's lots of different types of dwarf galaxies, but I'm not going to go into that. Okay, so we've got elliptical galaxies, spiral galaxies, dwarf galaxies. And where do galaxies live? Well, they live in the universe. We think there's billions of them, but they don't live by themselves. They live in pairs, they live in groups, and they live in clusters like this cluster here. This is a beautiful Abell cluster, 1689. And all of these galaxies are gravitationally interacting with each other. So under the force of gravity, they're being pulled in and they're moving around each other in this really dense area. Now, only about 5% of galaxies live in a cluster like this. We've got beautiful images of them because they've been a great thing for us to point our telescopes at because you get so many galaxies in one image. But most galaxies just live in pairs. They might live in groups of 3, 5, 10, and that's where we see most of the galaxies in the universe. But I couldn't resist showing this image because it's so beautiful. Okay, so we've got elliptical spirals, dwarf galaxies, and we know that they live in clusters, in groups, and they're pretty much, there's not too many isolated galaxies. So let's talk about what's in a galaxy, in a typical galaxy, in a normal galaxy, in a galaxy you'd seen in a textbook. Obviously there's stars, we've talked about that. There's gas, I'm going to show you a few more images of gas in galaxies. I'm going to spend a majority of the talk talking about the gas actually. There's dust, which I'll go to in a second. Dark matter, and if you were at the first lecture in this series you would have learned all about dark matter. I'm going to talk about it in terms of its gravitational effect, not so much of its properties. Planets, asteroids, meteors, cows, there's lots of things in our galaxy anyway. Do not tweet that I've said there's cows in other galaxies. That is not a scientific announcement. But there's the majority of things are listed on this side that are in a galaxy. And it's all held together by gravity. These are the assumption. This is the a priori that we have for a galaxy. And what we're going to do is turn that on its head and think, well, when is a galaxy not a galaxy? Throughout the talk, not right now. So when we're thinking about all of these different components, how do we actually observe them? So we've already seen the stars in galaxies. We know that we can observe them with optical telescopes like the Hubble telescope, but with your eyes, actually, you can just leave the city and look at a galaxy just from your backyard. What about the gas? What about the dust and the dark matter? How do we detect all of these components? Well, all of these components, apart from dark matter, emit in the electromagnetic spectrum. And this is just something, if you're older and have left school, you've probably seen it in school. If you're young and you may not have seen it, it will be coming. But the electromagnetic spectrum is just how the spectrum of electromagnetic radiation that we actually can observe. It can go from, from long, there we go, we're back. Long wavelengths and very low, low frequency, long wavelengths, low energy in radio waves, to very high energy, high frequency, and short wavelengths at the gamma ray end. And astronomical objects actually emit across this whole spectrum. So the thing I'm going to talk about is radio waves, and radio waves from a particular part of a galaxy, the gas. But we can also see the stars, obviously, from the visible light or the optical light. We can see things like the centres of galaxy clusters in X-rays, because there's so much energy when galaxies, massive galaxies, are colliding. They actually heat up the gas and it emits in X-rays, so you get really high energy X-rays. And infrared, we're going to have a look at some infrared images. That really is where we can see the dust. But of course, not all of this radiation actually makes it to the Earth's surface. This is good. We actually don't want to be standing here on Earth and having X-rays and gamma rays like falling on our heads, so it's really bad for our health. So luckily our atmosphere and magnetic fields and so on do block a lot of radiation from space. But what does come to Earth is radio waves and optical light. So there's two windows there that really do come straight through the atmosphere and into Earth. Otherwise, we need to put telescopes either really high on mountains, or we need to put them in orbit, and that's like the Hubble Space Telescope. Obviously we get optical light on Earth, but we get a better picture when we're outside the atmosphere. And what I'm going to just show you now is the dust in galaxies. And can anyone tell me what this telescope is? Yeah, everyone's saying, oh, JWST, James Webb Space Telescope. I wear it on my lapel. It's really revolutionising our view of the structure of galaxies, of so many different things. I'm sure, like you, like me, you're on the website the whole time. But this is, I'm going to show you two spiral galaxies. Now, think back to the one that I showed you earlier, where we saw the stars in the spiral arm and the dust lane which obscured all the starlight. And we could see the red in the centre from those old stars, and we could see the blue in the outer edges of the galaxy. What we're seeing now is more the dust. And you can see the centre of this galaxy here. But then look at these beautiful edges. You can see this structure on the edges of this galaxy here. I'm just going to go to the next one, because we've just never seen structure like this in a galaxy before. It's absolutely incredible. And I just really want to know what's happening over in this down here with this big hole. I want to know how big do the holes get? Why are they there? Are there star-forming regions in there? Is it where there's just lacking, where's the gas? Where does it line up with the stars? There's so many questions from something like this, and we don't really have simulations, I don't think, quite on this scale as yet to match it up. So it's given us a lot of things to think about. So we know how we can see stars and we can see dust in galaxies. And I'm just going to show you the Milky Way, so our own galaxy in these different wavelengths. So here it is in stars. Once again, you can see that dust going right through the middle of the Milky Way. Here we are in infrared, so the dust is now sort of standing out more. We can actually see that radiation from the dust in the Milky Way. And this is radio light. And now we're going to move into a new regime. We're looking at the gas in the galaxy. And in particular, this is hydrogen gas in our own galaxy. So you can see that our galaxy is full of hydrogen. There's hydrogen everywhere in this galaxy, all across the centre of the galaxy, and then it actually covers the whole sky. And we've also got these two little things down here, those two little features down the bottom. Does anyone want to hazard a guess what they are? Yeah? Magellanic Clouds, exactly. So two nearby galaxies to us, we can actually pick them out beautifully in hydrogen down the bottom here. So just as a refresher for hydrogen, I was talking to an atomic physicist earlier and he seemed a little disappointed that I was only going to be talking at the first element of the periodic table, hydrogen. But he did tell me about the Lamb effect. I hope I got that right, wherever you are. And neutral hydrogen, H1, this is what I call hydrogen. Hydrogen is just really light. It's the most populous atom in the universe. About over 70% of all our baryonic matter, so all of our atoms, is hydrogen. So it's a good thing to know about. It's also the fuel for stars. So the major fuel for star formation is hydrogen. And if you want to know what it looks like in its atomic form, it's literally just a proton and an electron. And don't worry too much about the next bit, but they have protons, electrons, they have a spin. Every now and then the electron will flip its spin, it goes down to a lower energy state and it emits a radio wave at 21.1 centimetres. It's about this long, so it's quite a big wavelength. It's 1.4 gigahertz, and we can actually detect this using radio telescopes. So a bit like as you tune your FM radio in your car, we can actually tune into hydrogen in the galaxy using a telescope like Parkes Radio Telescope. It's big because the wavelength of emission is big. So if you want to get any detail of it, you have to have a really, really big telescope. So in comparison, optical wavelengths are at nanometres, like very, very small. So you don't need as big a telescope as 64 metres, although people are building them that big. Okay, so let's have a look at some hydrogen in galaxies. Here's that same galaxy I showed you before, M1, Messier 101. This is what it looks like in star formation, and this is what it looks like in hydrogen. So we can see the hydrogen pretty much follows the stars, it follows the spiral arms, but look how far it extends out from the galaxy. And we think it actually will probably extend much, much further than this particular image as well. Here's a little dwarf galaxy, and the hydrogen, a huge disk of hydrogen that we don't really detect any stars in surrounding this galaxy. Here's the Magellanic Clouds again, and if we have a look at them in detail, we can actually see that those Magellanic Clouds seem to be interacting gravitationally. There's a big trail of gas and a leading arm of gas which is actually falling into our own Milky Way galaxy from these two galaxies. And this is the whole of the night sky in hydrogen. So this big blue part is our own galaxy, the Milky Way, and then this coloured part is the Magellanic Clouds. And you can see that the Magellanic Clouds hydrogen stretches right across the sky. So if you had radio eyes and you went outside, I mean, you'd need eyes as big as Parkes Telescope to see this, but bear with me, like you'd see this, it'd be amazing. So what about in interacting systems? So here we've got a flipped image where the dark is actually the stars. So this is 3 galaxies in the M81 group. This is the starlight, but when we look in hydrogen, we see they're interacting. We couldn't see that with the stars, with that particular image. Deeper imaging you can see a bit more. But we can see directly with the hydrogen, and that's being pulled out of the galaxies, and so we know those galaxies are interacting with each other. What about these? Beautiful. This is M51, Interacting Galaxy System. And you can see that spiral galaxy interacting with the galaxy above, and you might just be able to see the faint wisps of starlight there. What about in hydrogen? Look at, it's just, extending way more than what we would have thought. And so we're just seeing these are violent effects from just from gravity, pulling this gas out of the galaxies. And then it just makes you think, like this is NGC 2915, yes. One of my favourite galaxies. It's a dwarf galaxy, and the stars in that galaxy are just right in the centre there. We don't really detect too many stars anywhere else in that galaxy, but it's got a huge disk of hydrogen. And when I look at something like this, I think, well, what happens if the gas wasn't dense enough to form stars in the centre of that galaxy? Could we just have a galaxy that is just that disk without the stars? So we know that stars form when hydrogen becomes dense enough and hot enough for fusion to start. So it has to be really very, very dense actually, and hot, and that is basically falls under gravity. And so what if there is just a diffuse galaxy that has hydrogen and we don't have any stars? So that is where I sort of start getting interested in the idea of a dark galaxy. And then when we think about where is the hydrogen in galaxies and in the universe, what we can see are things like this, where we have two galaxies. You can see the white areas of the stars. Once again, that dot, all those dots are from our own Milky Way, so don't worry about that. But the blue areas are the hydrogen. And so in between these galaxies is a lot of hydrogen. We'll go on and there'll be a few things. Here's another one where we've got a huge tail of hydrogen. What I want to know, here's one where we've got a big cloud of hydrogen next to the galaxy. Here's one we've got a big ring of hydrogen. And so you start to think, well, some of the gas that we see may be just pulled out from a galaxy, or maybe, that big blob next to that galaxy has other components. Maybe it has dark matter, and maybe it is a galaxy itself, but it just doesn't have stars. So that's what I'm trying to explore in this research. Here's two clouds that I found. So this one, let me see if I can get this one here. I found in 2000, and I was at the telescope in New South Wales, and I took this image and then I overlaid the image of the hydrogen on top of the stars. So that's two images there, one made with a radio telescope, one made with an optical telescope. I overlaid it, and every single other time I've done this, there was a galaxy there, and this one there was no galaxy, and I just went, oh, I've got it wrong. And there happened to be a senior observer in that observatory at the time, and I said, what do you think? And he said, there's no galaxy there. You've found a hydrogen cloud. We don't know what it is. We'd never found this before. And we think this actually might be a cloud from our own Milky Way that's travelling at much, much faster than we would have expected. So it looked like it was an external galaxy, but we think it might be a cloud from our own Milky Way. Amazing, but we're not 100% sure. This one here, it's a cloud that we haven't seen stars before. It's next to another cloud which has a little galaxy in it, and which is 10 times less hydrogen. And so it's next to a galaxy, but it's a cloud of hydrogen. And so we just don't know, is that a dark galaxy, or is that some leftover fluff from the formation of this system? So that is something that we're really, really interested in. And here's one that we found, a cloud that was found in 2005-ish, and it was found near the Virgo cluster. At the time it was published as a dark galaxy. We found a dark galaxy, and the media absolutely loved it, of course. Astronomers find a starless galaxy. It was very, very exciting. Astronomers detect first invisible galaxy, or astronomers find absolutely nothing. So, this topic, just because it's dark, I think people get a little bit excited about the idea of what is it, and this lecture stream is on the extremes. So this is really looking at the extreme end of galaxies. So this is where I want to bring in dark matter, because we've talked a lot about galaxies and what's in a galaxy and what is a galaxy. And then we've seen a lot of hydrogen, and what we really want to know is how many of these components do you need for a galaxy? And the one thing that I haven't mentioned is dark matter. Now we observe dark matter through the gravitational impact. And so we have not detected a gravitational, oh, is that me? Sorry. We have not detected a dark matter particle as yet. But what we know is that if we look in a galaxy, so this is a beautiful spiral galaxy, the galaxy is rotating. So a spiral galaxy will rotate, we can measure how fast it's rotating, and we can plot that. So oh dear, sorry, that might be my hair. When we plot the galaxy rotation, these are my other two plots, you'll see this is the distance from a galaxy and how fast it's rotating. So I'm just going to pop up that so you can see the direct correlation there. So this is half of the galaxy plotted here. Now, if we were had the expected rotation, we would see something like this. But what we see is a rising rotation curve, what we call a rotation curve, and then it's flat. So the things that are moving at the edge of the galaxy move pretty much at the same speed. And what this tells us is that what we can do is then add up all the mass that we see. So we add up the stars, we add up the gas, we add up the dust, and then we work out what we think this curve should look like, and we have a gap. This was really how dark matter was discovered. And this amazing person, Vera Rubin, did this using stars actually, and really tied, the idea of dark matter came earlier, but Vera Rubin really tied down this idea of dark matter in galaxies themselves. So what we think is that, and when I'm thinking of a galaxy, I'm thinking of something that is seeded from dark matter. And when we look in the universe, we can actually map our galaxies over in space, but also in distance. And we get a map a little bit like this one. So every dot on that map behind me is one galaxy, and the I guess the x-axis on that hourglass is distance, and then the dome is just where it is on the sky. So you're seeing things that are further away as you move out from the centre. And you can see that it's like a web. And so our theorists have then tried to reproduce this web using computer simulations and physical laws. And you do something a bit like this. And in fact, you'll see, it'll happen twice and then it'll stop. You can see that we get that spiderweb vision from our simulations. So in fact, this is just using dark matter. There's no gas or stars in that particular simulation. What they've done is just use dark matter and let it put in seeded it basically, and then it just evolves over time under gravity, and this is what we end up with, and it's remarkably close to what we actually observe. The way we do it is using supercomputer. We've got one at Swinburne, there's supercomputers all around, and we add in some physics and a bit of dark matter, and you make I'm not a theorist, but this is pretty much how you do it. And you end up with the universe. Now, you can, I thought I'd remove that, but anyway, it's there, it's pretty. So we'll just look at that. So what we can do then is, okay, so we've matched up that the structure looks about right, but actually, we actually know the mass of every one of those little blobs of dark matter in the simulation, and we know the mass of galaxies, and we try to then correlate the two. And it's an imperfect science, but we do our best. And when the theorists did this about 15 or 20 years ago, what they found was that the simulations predicted about a factor of 2 more dwarf galaxies than what we actually see. And this was called the missing dwarf problem, or the missing galaxy problem. And one of the ways of basically filling that gap is by invoking that we have lots of dark galaxies out there that we just have never observed. We can test that theory. There's a few things that could be happening here. One is that we've just got incorrect physics. It could be that the galaxies are really faint, and in fact we are finding some really ultra diffuse galaxies like this one down in the bottom corner here, where you can barely see them. It's only because we've got brand new telescopes that can see much, much deeper and also a much more wider view that we can actually even see these things. So there's probably a whole population of galaxies out there that do have stars, but they're just very, very faint. Or that the galaxies have no stars. So maybe they have dark matter and gas, or maybe no gas, but let's just say for the sake of trying to detect them, that they have gas, but they haven't formed stars like that NGC 2915 without its centre. And so this is what I've spent my career doing, is searching for hydrogen in the universe. Now, to search for hydrogen, we can get our radio telescope, and if we knew where every galaxy was, we could just point the telescope at the galaxies, and then we measure the hydrogen, and then we know everything. But we know that we can't see all the galaxies. This is more like what galaxies look like. We can see the bright things, but we just don't know where the hydrogen is in the faint things. So we're missing all of those galaxies. So what we actually need to do is survey the whole of the night sky. Here's some telescopes that we use to survey the sky. Parkes, the Lovell Telescope at Jodrell Bank Observatory, the FAST radio telescope that's 500 metres. I mean, you just cannot imagine how big that is. It's an enormous telescope. That's me sitting on the edge of it there. And the Green Bank Telescope in West Virginia. All these telescopes have been used to survey the night sky for hydrogen. But when we look at hydrogen with these telescopes, what we get is what I called in my PhD blobology. Basically, you can't really resolve the gas very well because they've got they're big, but they're not big enough. And the limit for how big you can make a radio telescope is about that FAST limit. 500 metres is about as big as you can get. And that telescope, you can't move it. It's in a valley. You have to actually move the receiver above it. So what we do instead is we build lots of little telescopes and we link them all together, and then we survey the night sky using those. And the distance between the two furthest apart telescopes gives us basically the best resolution for that telescope. So we can link them all together as if it was a bigger telescope. This is the Australia Telescope Compact Array. It's just outside of Narrabri. So if you're ever driving to Brisbane, you can pop into Parkes, visit the Parkes telescope, you can go to Siding Spring, and then you can continue on and at Narrabri go and visit the Australia Telescope Compact Array, and then continue on to the theme parks in Brisbane. You'll be sorely disappointed after all those telescopes, but that's okay. This is the very large array in New Mexico, 27 dishes. It has baselines of kilometres. At the moment, this is just for the image, they're all close together. But these actually can be moved, and to have a simulated telescope that could be 6-10 kilometres or more in size. There's no way we could build a telescope like that. But the most exciting thing is that we have just built a brand new telescope in Western Australia called the Australian Square Kilometre Array Pathfinder. This is the Pathfinder 2, the Square Kilometre Array telescope, as the name suggests, but it's made out of 36 antennas in the desert, just outside of Geraldton. This is sort of what the landscape looks like. And you might think, well, why is it so far remote? And you can just sort of imagine if you tried to build a radio telescope in Melbourne, how much radio interference there would be. I mean, there's not only the radio stations, but everybody's mobile phones, all of your Wi-Fi, everything that is all air travel now is really, it's kind of killing our astronomy. So we have to go to the desert. This is actually in a radio quiet zone now. It's a zone where you're actually not allowed to turn on your mobile phone. The zone is about the size of the Netherlands and has about 250 people and, I don't know, 250,000 sheep, I don't know. So this is a beautiful image from Alex Cherney of the telescope at night, and I mean, I couldn't resist with the Milky Way bringing us back to the start of the lecture there. So you can see some of the 36 antennas there. And the beautiful thing about this is that this telescope just doesn't point in the night sky, and usually with a radio telescope we can just see a really small area on the night sky, and if you want to scan the whole night sky, and I have actually done it as part of a project that I did for my PhD with a team of 100 astronomers, is we used the Parkes telescope and we did this. We did that across the whole of the southern sky 5 times. So we had to drive the telescope across the whole sky 5 times to be able to survey the whole sky. But what this telescope does, press the wrong button, rather than just looking at the bright things, it just looks at really large chunks of the sky, 5.5 by 5.5 degrees across the sky. So we're much, much faster in actually observing the night sky. And that's all from this beautiful piece of technology here called a phased array feed. We call it a PAF, so if you want to be cool amongst your friends, you could go, I'll learn about the PAF today. That's what it looks like, and it allows you to look at a really large part of the sky at the one time. And that means the survey speed's faster, we're going to find more galaxies, and we're going to actually be able to go much, much deeper as well. This image didn't come out too well on the back here, but this is one of the first images that we've taken with the ASCAP telescope looking at hydrogen, and every one of those this is not stars now, this is every one of those little dots is hydrogen. And you can see the enormous challenge that we have. This is just a small part of the night sky. There's probably 150 or more hydrogen sources there. And we now have to take every one of them and match them up with the stars that we see from other telescopes and with the dust and so on, to see whether or not is this something that we knew about? Is this a galaxy we already knew? Or is this a new piece of hydrogen that we never knew about? So that's a beautiful new piece of data that's just been released. And we're going to, and of course, the big question is, did we find any dark galaxies? And the answer, I didn't even give you any lead up to that, it's just no. But we have been finding a whole heap of gas that we just can't really account for. I'll show you a couple of examples. Here's one. This is actually using a telescope in South Africa where we found as much gas as about 10 Milky Ways would have, but there's no galaxies there. So there is a galaxy group, but it's right on the edges there. There's no indication where this gas came from. So it's a bit of a mystery. There's another one here. We found 2 dark clouds nearby another galaxy. Once again, we don't really have the models that explain these dark clouds. And here's another beautiful image where we're just seeing those gas streams once again. On the right you see the deep optical imaging, so we can see the starlight from the 2, that's working again. Okay, so the 2 galaxies there, and then when we look at them in hydrogen, there they are. So what we're going to do is survey most of the night sky in a survey called Wallaby, and that's going to find somewhere between 200 to 600,000 galaxies. And the beauty of this is that we're going to see the whole night sky, but we'll also have really good resolution. So we'll have that fine detail, so we can match those detections up to stars and to other wavelengths, other components of galaxies, to start understanding how common is it to find gas without any stars, and then, of course, the next step is looking at the dynamics to see, do we think there's any dark matter there? And that's going to be the real test for dark galaxies. In the future, we're going to have this beautiful telescope, the Square Kilometre Array. It's built over 2 sites, one in Australia and one in South Africa. The South African one is the one on the left. That's going to be the one that we use to look for hydrogen. We're expecting to detect a billion galaxies, not just through hydrogen, but through their galaxies' radio emissions. And on the right, you can see a totally different type of telescope, which these antennas are about this high, and they literally look like a Christmas tree. And that's going to be built on the site where ASCAP is, and that will be able to see back to just after the Big Bang and tell us about the beginnings of the universe. So we've got some very exciting times ahead. And so this is my final slide, really just to say that these observations of cosmic hydrogen, they're a very powerful tool to search for galaxies, but also to test our ideas about what is a galaxy, what makes a galaxy. And these next generation telescopes like ASCAP and the SKA are really going to revolutionise these fields. So I guess watch this space. Thank you.
Amazing. You slightly blew my mind. I have to confess, I had a slight preview because we spent some time chatting on last Sunday on Triple R with Shane Huntington about this. But the idea that there are galaxies that don't consist of stars at first was I was like, well, hang on, aren't galaxies defined as, clusters of stars? And the idea that they might, there might be galaxies out there that we literally just can't see because they're mostly dark matter and perhaps some dust. Just takes my mind in all sorts of incredible directions, and I'm so grateful to you for such a wonderful lecture. I'm sure it's also raised lots of curiosity and questions from our amazing audience. So we've got 2 microphones available, so if you'd like to raise your hand, and Matt will be available on this side with the microphone, and I'll go on this side. I'm going to run all the way up.
Thank you for the talk. Great. My question is not about hydrogen, but dust. When we talk about dust, are we talking about microns or moon size? Do we have a view on composition source?
Yeah, dust encompasses all of that, but mainly micron sizes and maybe a bit bigger. When we sort of talk about dust, that's the emission range that we're looking at there. Yeah.
Thank you very much. What if literally there are infinite number of galaxies, and therefore by definition obtaining information about them is impossible and it's unknowable?
Well, so infinite number of galaxies. What we know is the universe is finite in size. So we think that there are a finite number of galaxies within the universe. We can understand what we can see, so what we see in the observable universe. And that's what the tools that we're using as astronomers to understand. So it's really difficult for us to speculate what we can't see. There's people that do that, that think about things like the multiverse and so on. I'm definitely not getting into that here, but that's beyond the scope of what I do. What I'm doing is really looking at the galaxies we can see, and then when we get to 1 billion galaxies, what is it that we learn about the formation and evolution of these galaxies so that we can understand how do we get to today's point in time. And so that's what we're really focusing on in our astronomy. Yeah, thanks.
Thank you for such an amazing lecture. I was wondering if dark galaxies, say, did exist, whether it would prove the existence of dark matter and dark energy or not.
Yeah, well, that's a very good question. So it's almost like the reverse. To prove a dark galaxy, we'd want to know that it has dark matter. At the moment, we only see the dark matter through the motion of, through the gravitational interactions. And so it's possible that we have clouds of hydrogen. If it turns out I think we've got pretty good evidence for dark matter, but if there is no dark matter and we have a cloud of hydrogen that hasn't formed stars, we then have to think about what would be the physics to then classify it as a galaxy. So we're really getting into that regime of what is a galaxy actually, and that is something that we'll keep refining over time. So we've sort of started off with these really sort of block ideas of what a galaxy is, but as we learn more about them, I think that we'll be able to refine that question. That's a great question.
Thank you for the really amazing talk. My question was, are these hydrogen clouds composed purely of hydrogen? And if not, what would the repercussions of that be on this theory?
So it's really hard for us to find out what else is in a cloud of hydrogen. So hydrogen is great because it emits at 21 centimetres, but a lot of the other we call metals, but elements that might be in a cloud, we can only detect if we've got a source behind it and we see it in absorption. So we actually can look at some of the gas through absorption lines, and we do see that a lot of, there's a lot of metals in gas, including carbon, silicon, oxygen, whatever it might be. And so that would be something that we would really like to do for all of these clouds, but we can only do it when we've got that background source. That's really a limitation on what we have. It's quite possible that most of the gas that we see is actually polluted by earlier star formation, and that is indicated by a lot of the observations that we do, that we usually do see other metals in the gas. Yeah, that's a good question too.
I was just wondering if gravity waves would be in your purview in the future or something like that.
Well, it's in my purview only because they're amazing and I'm really interested in them, but they're, at the moment I haven't seen how they would relate to hydrogen in particular, but what they do give us is a new window on the universe, and so a new way of probing the universe. And I think as that field progresses, we're going to actually find new ways of trying to see how galaxies interact, but also just those physical laws that govern galaxies. Yeah.
That was a really amazing talk. My question is kind of two-pronged. So you explained very well that stars are formed when the hydrogen atoms are heated up and fused together. What differentiates a galaxy with stars and those without? Like, is there something going wrong in the fusion? And also, what implications does this have for our current understanding of galaxy formation, like stretching back to the Big Bang?
So what we know, and what we've done is observed where we have stars in a galaxy and where we don't have stars, and we can look at the density of the gas, and we see there's a critical density above which we seem to always form stars. It's not quite that simple, but there's a general rule about that. So what we think is that the gas that's too diffuse doesn't form stars, and when it gets to a critical density, then it gets overcome by gravity, and then it sort of spirals into actually forming stars. Now, what is very interesting when you're thinking about diffuse gas is that galaxies don't live by themselves generally. Like, you have galaxies, as I showed, they're in filaments and they're in clusters, they're in groups or whatever. So what happens to that gas? We're talking about neutral hydrogen here that is emitting at 21 centimetres, which means it needs to have an electron in its atom. So what about gas that might have a bright neighbour next door? Is that going to somehow erode away the gas? Is that gas going to be dissipated? Will it hold under gravity? These are questions that we are looking at theoretically. There's some theory that says, you actually can't have a dark galaxy because all the gas would basically be evaporated, for want of a better word. But there's other theories that don't say that. And so I think that's why we're really looking at that, because we're not 100% sure of the answer of that question. Thanks.
Hi, I was just wondering, is there any particular reason that we see these web structures emerging as opposed to just like big clumps?
It's just due to gravity and also the, I guess, in the early universe, there were really slight perturbations, and so just matter perturbations, and that's where we started to see things form. So these webs and so on, they come out naturally from the simulations, just from those initial perturbations. And we know about the perturbations because of the cosmic microwave background. We've actually got some idea of what those perturbations look like. So that's why we can sort of simulate things so well. So there's no real answer other than it comes out from the physics. Yeah.
All right, to save time, I think we've got time for one more. Is there one question? I went straight up, so finish with all that.
Before, when you mentioned about dark galaxies, you meant the clouds of hydrogen. You mentioned that it's possible that they were spewed from a galaxy. You want to differentiate between whether the hydrogen cloud formed by itself or whether it's from another galaxy. So my question is, does a dark galaxy have to be formed by itself, or can they also be coming from another galaxy?
Yeah. That's a great question, because we actually have things called tidal dwarf galaxies, which we think are actually formed out of gas that's come out of galaxies. So that question, could that gas be a dark galaxy? I guess we'd have to then think about what would all the components that we need in a galaxy. Maybe we need 2 out of the 4 components, I don't know, like dark matter and stars, or dark matter and gas, or stars and gas. I'm not 100% sure on that. But what I'm really interested in is those early seeded dark galaxies that might be from the dark matter, where you might just have had hydrogen sitting there for the age of the universe and it hasn't formed stars. So I think that's a really great question, really cuts to the bone of what is a dark galaxy. But when I'm thinking of dark galaxies, I'm really thinking of those what we'd call primordial clouds of hydrogen, and that would be something amazing to find. Thank you.
All right. Thank you so much for such a great
these are for you. Oh God, thank you.
Thank you. Keep going now. It was a wonderful lecture. Thank you. I'd be pleased if any of you would like to join us for the final lecture in our series next week, which is our very own from University of Melbourne, Associate Professor Katie Orbital, who will be unpacking a stellar crime scene and talking about the extreme sort of life and death of stars. So we're going from galaxies to stars themselves next week. Thank you all for coming along, and have a wonderful evening and a wonderful weekend. Thank you very much.
Oh, thank you. That's so cute.
The least I can do. I know it doesn't pay